that exists in a tube of air. When we studied the wave on the string, the key was to realize that since both ends of the string were fixed, each end has to be a node of the oscillation, because there was no amplitude of oscillation at either end. This is called boundary condition. That's what happens at each end of the string. What we have here is a similar situation, except the medium is no longer string, but rather it's air. Consider a tube with one end closed and the other end open. Now suppose there is a sound wave propagating into it. What happens when it meets this closed end? Well, this acts like a wall, so it bounces back, right? So you got one wave going in, another wave bounced back. You got two oppositely traveling waves, and of course the result is a standing wave, just like on the string. Okay, so what we have is a standing sound wave. What we need to know is what are allowed frequencies and wavelengths that can exist on this pipe. To figure that out, we use something similar to the case of a string, the wave on a string. That is, let us take a look at what happens to the sound wave at those two ends. Okay, now from the previous chapter, the physical nature of the sound wave can be understood either as a pressure wave or as a displacement wave, right? You think of the pressure wave because the pressure of air due to the presence of sound is no longer uniform throughout. Rather, on top of the ambient pressure, there's a slight variation of air pressure that propagates like a wave. Okay, so that is called pressure wave. The reason why there's a pressure modulation, there's a pressure wave, is because as the air molecules move back and forth, they cause air to be locally compressed and locally decompressed. Where the air is locally compressed, you have slightly higher air pressure than the surrounding, and when the air is locally decompressed, you get a slightly lower air pressure than the surrounding. Okay, so you can also think of the sound wave as a displacement wave. Here the displacement refers to molecular displacement. Okay, so we're looking at the collective motion of molecules going in like this or going out like that. Okay, if they go in like this, that creates a local high value of pressure, and if they go out like that, that decreases local pressure. There is a relationship between the pressure variation and the displacement S of the sound wave. This equation is copied from the last chapter. Here, B, as recall, is the bulk modulus. Okay, you notice the interesting thing here, and that is delta P, the pressure wave, is not directly proportional to the displacement wave S. Rather, it's directly proportional to the derivative of S with respect to location. Now that sort of makes sense. Okay, now what that means is that if this is a sine function, if S is a sine function, delta P is a cosine function, they differ from each other by a phase of 90 degrees. So when one of them is 0, the other is actually maximum. How does that make sense? Well, because imagine if the air moves in like this, right? They move in like this. Of course, that's going to create a local higher value of pressure. So you get a pressure antinode. Okay, but as the air come in, they are compressed towards each other. They got no place to go, so the displacement is actually 0. Okay, so you have, in this case, 0 displacement, but great amount of pressure. So indeed, when one is a sine function, the other is a cosine function, qualitatively that makes sense. Okay, so let's take a look at the pressure or the displacement wave of the air column due to the sound produced as a standing wave inside this fluid, inside this tube. First of all, let's look what happens at the closed end. Now, it is clear that at the closed end, the movement of the air molecule due to the sound is like this, right? But when they hit this wall, they got no place to go, right? So what is the displacement of the longitudinal air wave S at that location? Well, they wanted to go this way, but they cannot because a wall stops them. So S is 0. Okay, so this obviously is a node of the displacement. Node of displacement. All right. What about pressure then? Well, the pressure, according to this expression, if this is a node, then that would have to be an antinode, and that makes perfect sense because what that means is that the air molecules are congregated here. Okay, once the air molecules come in like this, they got no place to go, so they all stopped here. They all trapped here. There is a local, of course, increase in the density of the air molecules. That, of course, increases the pressure at that region. So you will have a pressure antinode at this location, yet a displacement node. Okay, when I use node here, I'm assuming that I'm treating this as a displacement wave. Please do not confuse it with pressure wave. They're equivalent to each other, but if you want to think of this as a pressure wave, that this is an antinode. Okay, it is a maximum value of the pressure. Now, what happens at the open end? Well, at the open end, the air pressure here is linked to the air pressure outside, right? Because it's exposed to the air outside. So you can imagine, you don't really have a lot of variation of air pressure air pressure here. The air pressure pretty much is just the ambient pressure. So this would be a pressure node, and therefore it's a displacement antinode, which means the air movement is the largest. That also makes sense because, after all, the air molecules, when they reach this region, they're open to the air outside. Of course, they can move freely. Okay, so this is a displacement antinode, and the closed end is a displacement node. Okay, knowing this will greatly help me draw schematic diagrams for the resonance that can exist in this tube. The idea here is that when you draw displacement waves, you have to make sure this closed end is a node and this open end is an antinode. Okay, so let me draw a few possibilities. Okay, so I have here a tube with one end closed and that end open. Let us draw the displacement air waves due to a presence of the sound. Okay, again, this would be a node, it's a closed end. This would be an antinode. So one possibility, which corresponds to the largest possible loop size, would be something like this. Right? After all, you have a node here and antinode there. Okay, now if you draw something like that, then you realize this is only half a loop, right? Because if I extend the other half, I get a whole loop, right? So the length L in this case would have to be only half a loop. Now, how long is each loop in terms of wavelength? We learned that is half a wavelength, so this is actually lambda over 4. Okay, in other words, this wavelength is 4 times the length of the pipe. We call it lambda 1. That is the longest possible wavelength. Okay, lambda 1. So lambda 1 equals 4L, and what is the corresponding frequency? Well, the longest wavelength corresponds to the lowest frequency, right? So what's F1? This is the fundamental mode, or the first harmonic, corresponding to the lowest frequency that can exist in this pipe. That would be V over lambda. V is the speed of sound in air over lambda 1. Okay, now lambda 1 again is 4L. Okay, so that would be V over 4L. Fundamental mode. Now, next, let's draw another possibility. Again, we want to keep this end a node and this end an antinode. So how about something like this then? All right, now, right, that works too. Node and an antinode. But this time I have squeezed in 1.5 loop in between the same length L. And therefore, I say L equals, this time, 1.5 loops. In other words, 3 over 2 loops. And you know each loop is half a wavelength, so this will be 3 over 4 lambda. And that is the wavelength for the second harmonic, or lambda 2, and that allows you to find F2, the second lowest frequency that can exist in this pipe, and that would be V over lambda 2. So what is that equal to? Well, actually, you see lambda 2 is 3 times as short as lambda 1, so therefore this would be 3V over 4L. Okay, and you notice this really is just 3 times F1, right? 3 times F1. Okay, let's keep on doing this. We make the loops even shorter, so this time I'm going to include 2 full loops, and then plus half a loop at the end. I must have a half loop at the end because I want an antinode at the open end. Okay, so this time what do we have? Well, this time L equals 2.5 loops. Okay, and so that's 5 over 2. times lambda over half a wavelength. This is lambda 3, right? And so the corresponding frequency, f3, what's that equal to? Well, that would be 5 times f1, right? So this would be 5v over 4L, and so on. Okay, you get the picture. You got the lowest frequency, a fundamental frequency, and the second harmonic is 3 times as high in frequency. The third harmonic is 5 times as high, and so on. So in general, what kind of frequencies can you produce on this pipe of length L with one end closed, the other end open? That would be F equals to Fn, okay? 1, 3, 5, so in general it's 2n plus 1, right? 2n plus 1. V, speed of sound, over 4L, okay? N equals, the lowest n is 0 because, you know, that will be, you have a 1 left, that's corresponds to the lowest frequency, 0, 1, 2, and so on. Okay, this is how we can use a pipe of a certain length to select a frequency we want to produce. You see, the frequencies that can exist on this pipe depend on 2 things, okay? One is the speed of the sound, the other is the length of the pipe. So by choosing the length of the pipe, we can figure out what kind of frequency that can be produced. Again, the key here is to make sure you know the closed end is a node and the open end is an antinode. You know, you don't have to remember those formulas mechanically. All you need to do is to understand what happens at the boundary. Okay, closed end, open end. Then you can just start to draw these pictures, right? And then you get a whole bunch of loops, and each loop is half a wavelength. That allows you to figure out the wavelengths. And once you know the wavelengths, you can go ahead and figure out the corresponding frequency. Now, what if I change the situation at the border so that this time I have both ends open? Okay, instead of a closed end and open end, I have both ends open. This would correspond to a flute. Okay, so here is a situation like this. You have, you're playing a flute. Okay, and this flute has both ends open now. You look at this structure here. This structure is for you to blow air in, okay? Just to blow air in so that you can start a vibration, okay? That's all there is to it. But essentially, see, this is open to the outside, right? So this is an open end. This is also an open end. Remember, an open end corresponds to an antinode of displacement. So you must make sure this is an antinode, this is an antinode, right? And how do you draw something like that? Well, this will give you the longest possible loop, right? You get antinode, antinode, of course there's a node in the middle, and here is the next possibility. You have an antinode here. So you see, the idea is you must have a half loop at each end, okay? And in between, you can put in 0 loop, 1 loop, 2 loops, 3 loops, whatever you want to do. Okay, now, what about the corresponding frequencies? Well, this is half a loop, this is half a loop, I'm sorry, yeah, this is half a loop, this is half a loop. So you add them together, you get 1 loop, right? Now 1 loop, what is the total length? Okay, the total length is L, and that also equals half a wavelength because it's 1 loop, right? So you see, L equals lambda 1 over 2 because it's half a loop. I mean, this is half a wavelength for 1 loop. So that gives you lambda 1, which is 2L, and that allows you to find F1, which is V over lambda 1, V is the speed of sound. Okay, that is V over 2L. So this is how you find the first harmonic that can exist on a pipe with both ends open. Okay, here is the next mode. You put in a whole loop in between this half a loop at the end and that half a loop at the end. Okay, so what you have here is half a loop plus 1 loop. You have a total of 2 loops instead of 1 loop. So you cut the side of the loop by half. Therefore, lambda 2 instead of 2L now becomes 1L. Okay, 1L. And from that, you can find the frequency. That frequency turns out to be twice as much as the first harmonic because, you know, the wavelength is halved. Okay, so here's the second harmonic. And then you have the third harmonic and so on. You can do this calculation. Turns out the third harmonic is 3 times in frequency compared with the first one. Okay, so this is when you have a loop with both ends open. Here again is a situation that we discussed earlier, except this time the drawing is more professional. This is actually a real pipe. you have one open end, one closed end. The open end is shaped like this so that air can flow in. Okay, so this is an open end. Again, you have a node at the closed end for displacement, and an open end at the open end, and so on. The calculation goes like what we had before. And you notice the interesting thing here, just like we discussed before, the third harmonic is 3 times in frequency as the first one, and the fifth harmonic is 5 times in frequency as the first one, and so on. Okay. Now, what if both ends of the pipe is closed? Well, if you manage to get an air vibration inside with both ends closed, this time both ends must be a node of the frequency of the sound wave displacement. So you have is something like this, okay? Right? Both ends closed. Or you can have something like this. Or you can have something like this. You get a picture, right? So the first harmonic would correspond to half a loop. Second harmonic would correspond to 2 loops, and then you have 3 loops, and so on and so forth. You notice that this really has the same mathematical formula as the case when both ends are open, right? Except when both ends open, you have to draw it slightly differently, like this, right? And you draw it something like this, and you go something like this, right? But if you add the total lengths, okay, here is 2 half loops forming 1 loop. Here is 2 half loops plus 1 whole loop. That's 2 loops. Here is 2 half loops plus 2 full loops plus 2 half loops. That's 3 loops, just like this, right? So with both ends closed, the formula for the frequencies and the wavelengths will be actually the same as the case when both ends are open. So you see, you don't have to memorize these formulas mechanically once again. You just have to know 2 things. First of all, what happens at the closed end and what happens at the open end. And then you just have to draw the these diagrams for nodes and antinodes and make sure that you know that each whole loop is half a wavelength, each half a loop is a quarter of a wavelength. Okay, so from that we would know how to choose the frequency that can be produced by a column of air. Another interesting phenomenon is called beats. This is otherwise known as interference over time, not over space. Okay, what do I mean by that? Well, suppose I look at 2 oscillations happening at the same moment. Okay, this time I don't use the regular resonance condition. Regular coherence condition, which means the two waves must have exactly the same frequency and so forth. Rather, I consider there is a slight variation in their frequency. So the first wave has an angular frequency omega 1. The second one has an angular frequency omega 2. Now, I want omega 1 and omega 2 to be slightly different from each other. However, I don't want them to be very different. Okay, so there's a slight difference only. And for simplicity, let's say they have the same amplitude. Okay, so for example, you can play 2 tuning forks. Okay, say they differ by, say, 1 or 2 hertz. Okay, so here is the sound produced by tuning fork 1. Here's the sound produced by tuning fork 2. Now, what if you bang these 2 tuning forks simultaneously? What are you going to hear? Okay, what you hear is something interesting. It's called beats. Let's look at what happens. You need to add these 2 cosine functions together. And here is the formula from your high school math. Okay, cosine alpha plus cosine beta. Here's the formula. Alpha is omega 1t. Beta is omega 2t. So let's plug this formula in and let's see what happens. So when I have both of these 2 sources playing simultaneously, I get y equals to, all right, 2a, and then cosine, all right, alpha minus beta, so omega 1t minus omega 2t divided by 2, right? Omega 1 minus omega 2, we call it delta omega, okay, times t over 2, right? And then there is a cosine function again. This time is alpha plus beta over 2. So omega 1 t plus omega 2t over 2. Okay, now omega 1 plus omega 2 divided by 2. Isn't that the average value of omega? Okay, average omega times t. All right, here's the trick. The trick here is that delta omega is very, very small compared with the average value of omega. Let's say, let's say we have 2 tuning forks, one at 440 hertz, the other one at 441 hertz. Okay, so omega is 2 pi times 440 something. It's much, much greater than delta omega, which is only 2 pi times 1 hertz, right? So what we have here is the product of two cosine functions. They both vary with time, but they vary at very different rate. This one varies with a angular frequency of delta omega over 2, which is much, much slower than omega bar. Okay, so this omega bar varies very quickly, and that one varies a lot slower. So what we can effectively do is to think of this whole thing as a time-varying amplitude, AT. Okay, so this basically is an oscillation of cosine function, okay, cosine function with the average frequency, average angular frequency, but its amplitude changes over time, or we say it is modulated over time with a slow time varying function to a cosine delta omega t over 2. Now, if we plot a t as a function of time, you find a slow varying function of time. Okay, here is the t-axis. This is the slow varying function. So it's like this. Okay, slow varying function. But of course, something's going on when the amplitude changes, right? And that is there is a cosine function. So the actual oscillation. Okay, this is y. Okay, the actual oscillation would be the product of the amplitude and this cosine function. This cosine function varies a lot faster, so you have something like this. Okay. Something like this. All right. Now we can look at a wave pattern like this. Remember, this is the t-axis, not the x-axis. Okay, so when you listen to these two sources playing at the same time, you find two things. First of all, you are going to hear pretty much the frequency of either one of them, because here is an average frequency. Remember, these two frequencies are very close to each other, so they only differ about, say, 1 or 2 hertz. So essentially, you are listening to something like 440 hertz. Okay, I mean, whether it's 440 or 441, most people cannot tell the difference really. But the interesting part is that the amplitude of this 440 hertz signal is not a constant. Rather, it changes over time. Like here, weak and then strong and then weak and then strong and weak and strong. There is a modulation in the amplitude or in the intensity. Okay, now let's see how long it takes to go from here to there. That, in fact, is a whole variation, okay? Is a whole variation of this cosine function. So, in other words, the phase angle of this cosine function, between here and there is 2 pi, okay? That would be the, the period of this particular cosine function. So, what is the period of this particular cosine function? The frequency of this term is angular frequency of this term is delta omega over 2, right? So, how long does it take to go from here to there? That you will have to take 2 pi divided by the angular frequency, right? So the time it takes to go from here to there, that will be 2 pi divided by this angular frequency, okay, which is delta omega over 2. By the way, at this point, let me introduce the frequency itself instead of the angular frequency. So omega equals 2 pi f. Okay, so in other words, delta omega really is just 2 pi delta f. So what's delta f? Is the frequency difference between these two signals, not the angular frequency difference. Okay, you divide by 2. What do you get? You cross out the 2 pi, right? You cross out the 2 pi. What do you get? You get 2 over delta f. That is the time it takes to go from here to there. But going from here to there, our ears have experienced 2 cycles of variation in intensity, right? Here we hear nothing, and then strong, and then weak, and then strong, and then weak, right? Now, if we are looking for the time it takes for the intensity that we hear to change once, okay, to repeat one cycle, then we're looking for the time to go from here to there, right? And that is half of that time, okay? So the time it takes to go from here to there for the intensity to vary one cycle, T, B. B standing for beats. T of B really is just half of this time. So T of B equals to 1 over delta F. Now, I can invert T of B to get the frequency of the beat. So what did that tell us? It tells us the frequency of the beats equals to delta F, which is F1 minus F2. Okay. This is a so-called beat frequency. In other words, if you have two tuning forks, one at 440 Hz, another one at 441 Hz, you play them simultaneously. You can pretty much hear something around 440, except that the intensity, okay, the strength of the signal varies at a rate of 1 Hz. That is called the beat frequency, because 441 minus 440, that's 1 Hz. So the intensity would go up, down, up, down, up, down, and a cycle at the rate of 1 cycle per second. Of course, 1 cycle per second, our ears are good enough to discern that. If it's 2 cycles per second, we can still count, right? We can hear the signal going up and down, twice a second, and even 3 or 4 we can do. But if the if the cycle if delta F is say 20 Hertz, that would mean that the intensity goes up and down, 20 times a second. That's kind of hard for our ears to discern, so we can lose track how many times it goes up and down. Okay, so to hear beat distinctively, what you need 2 frequencies, but you want 2 frequencies to be very close to each other, no more than a few hertz away from each other. This is called beats. Can you think of an application of this phenomenon, beat? What do we need that for? Okay, how about this? Suppose you make a living as a piano tuner. Okay, what you need to do is to make sure that you adjust the tension of each string. Remember, that's how we tune the piano, right? We adjust the tension so that the string produces the exact right frequency. Let's say 440 Hertz. Okay. Now, when the piano is being played for over some time, it's going to go out of tune. Sometimes the frequency gets a little too high, sometimes it's a little too low. That's why the tuner comes in to try to adjust the tension to make it go back to 440 Hertz. Now, how would the tuner accomplish that? If you strike that key, let's say the correct value should be 440 Hertz, okay? But in reality, it's actually 442 Hertz. Many people cannot really tell that much of a difference if it's 1 or 2 Hertz. If you have really sharp ears, you can tell, oh, this is a little bit higher in frequency than I wanted, so we say it's out of tune, so the piano tuner comes in. But no matter how good the tuner is, the tuner cannot tell exactly how many Hertz higher is this thing out of tune. Okay, he cannot tell whether it's 441 Hertz, 442 Hertz, or 443 Hertz, and so on. Okay, nobody has ears that good, that quantitative, So what do? Okay, what you can do if you're a piano tuner is if you bring in a tuning fork, which is exactly at 440 Hertz. And what you do then is you strike that piano key, right? That is 1 frequency. That's 1 source. And you bang your tuning fork. That's the second source at the same moment. All right. So if these 2 frequencies are different when produced by the string, when produced by the tuning fork, which is standard, what are you going to have? Well, you're going to hear a beat, right? Now, the beat frequency you can easily count, like 1, 2, 3, 4, so on. Let's say there are 2 ups and downs per second. What is that telling you? It tells you there is a 2 Hertz difference, okay, between the standard tuning fork at 440 and the string, which is out of tune. In other words, the string is either vibrating at 438, which is 2 Hertz below 440, or at 442, which is 2 Hertz above it. Now, how do you tell whether it's higher or lower? Well, there are many things you can do. For example, you can slightly increase the tension of the string, which slightly increases the frequency produced by the string, right? Produced by the first source, right? And then you look at the beats again. Okay, listen to the beats again. If the beat frequency gets lower, what does that tell you? It tells you delta f is smaller, which means, bringing the string frequency higher reduces the difference between the string frequency and the actual frequency, which is at 440 hertz, which means the string frequency was lower to begin with. Okay, so you increased a little bit, the situation improved. So what does that tell you? It was at 438 hertz to begin with, so you have to increase the tension, okay, to bring it up. And if you increase the tension and you play the beats again, you find the beat frequency increases. Okay, it becomes 3 cycles per second instead of 2. That means you're going in the wrong direction. Okay, it was already 442 to begin with. You just made it even worse. All right, so this is a simple application of the beat phenomenon. Here's one more diagram concerning beats. We said that the beat phenomenon is interference of two sources in time, not in space. Let's take a look and you will see what I mean. I have here two sources, one depicted in black, another one depicted in blue. Okay, look at this moment. You see, at this moment, the first wave and second wave, they're pretty much out of phase. See that? They're pretty much out of phase. So that the resultant frequency, the resultant amplitude is pretty low. Okay, it's pretty low. Now remember, they don't have the same frequency. So if they're out of phase, then they're not going to be out of phase all the time. Okay, they gradually go through different phase angles over time. If they make the frequencies exactly the same, then once they're out of phase, you have no luck. They will always be out of phase. But that is not the case. So as time progresses, at this point, they're still out of phase. In fact, at this point, they're exactly out of phase. So the resultant oscillation is 0 in amplitude. And then the blue curve has slightly higher frequency than the black one. Okay, so the frequency difference, the phase difference will change over time, and you gradually move forward. You see, at this point, the two waves are pretty much in phase already. All right, so you see the amplitude increases, right? And look at that point. How about that? At that point, both waves are up at maximum. They have to be in phase at this particular moment. Okay, so you see, the amplitude, the resultant wave is largest. And then, as time progresses, once again, they start to go out of phase, more and more, until at that point, they become exactly out of phase. One is up, the other down, to cancel each other out. Okay, so you have a minimum in sound intensity. So this is why you have this variation in intensity. It's because the frequencies being slightly different, these two waves can go from out of phase to in phase to out of phase to in phase to out of phase as time progresses. And if that happens slowly enough, let's say once or twice per second, we can easily discern it. So that's where the phenomena of beat come from. Okay, now let's look at briefly the issue of so-called complex waves. In other words, we're not just looking at a harmonic wave, sine and cosine wave. Okay, a complex wave, which is not necessarily simple harmonic anymore. We have a complex wave, but we still want to make sure the wave is periodic, which means it does repeat itself. It's not a sine or cosine function anymore. The idea here is that even though the wave is not harmonic, okay, it's not simple harmonic, what we can do is use what's called Fourier analysis. Okay, that's attributed to the French mathematician Fourier. What is Fourier analysis? A Fourier analysis takes any periodic function. Here's a periodic function, okay? The period is t. All right. Given that period, you can find the corresponding frequency, f, which is 1 over t. Okay. This is called f1. We call it the fundamental frequency. And then we can define f2, f3, f4, and so on, which is 2f1, 3f1, 4f1, and so on. Okay. So the idea is this. Here is a periodic wave with a fundamental frequency of 1 over t. Okay. If I use a simple harmonic wave, I'm not going to be able to use that simple harmonic wave to totally mimic the original wave, because the original wave is not simple harmonic. However, according to the Fourier analysis, even though a single harmonic wave is not going to do the job, what I can do is to use a whole bunch of simple harmonic waves. See, take a look. This is the sum of a whole bunch of simple harmonic terms, right? Look at the first term here, A1. Here's 2 pi f1t. sine function. Here is 2 pi f1t cosine function. So it can both be sine and cosine. Okay, so here I'm using a sine or cosine wave at the frequency f1 to mimic it. And that is not enough, so I add another wave with a frequency f2, both sine and cosine, and then f3, both sine and cosine, and so on. Turns out that for any complicated periodic wave of this period t, if I choose a sub n and b sub n wisely, appropriately, I can always use these sine or cosine waves to represent any of these waves. Okay, in other words, if I choose A1, A2, A3, A4 correctly, all right, I can use these sine cosine waves to exactly represent any non-harmonic but periodic wave. Now, why is this important? Because periodic waves are because simple harmonic waves are simple to study, but they're boring, especially when it comes to music. Here is a drawing for a simple harmonic wave like this. Okay, it's got a certain period, okay, from here to there. It's got a certain period t, of course, corresponds to a certain frequency, f1. Okay, if a wave behaves like that over time, when you hear this wave, it's not going to be very musical. It sounds like what? Like a tuning fork. Okay, a tuning fork is designed to produce only one frequency. Okay, it doesn't sound terribly good. Now, here I have a different type of wave. It has the same period as that one. Okay, same period. I mean, I didn't draw it very well, but my intention is to draw the same period as this one. But you see, the form is not simple harmonic anymore. There are some wiggles here. Okay, some wiggles here. And when you play a musical instrument which produces a wave like that, you compare this with a tuning fork at the same frequency or same period, you will find that you're playing the same tune. Okay, you're playing the same note, but it's going to sound a little different. Why? Because this wave is not simple harmonic. As a matter of fact, if you use a different musical instrument to play the exact same tune, you got to have the same exact period, but this time the waveform is again different. Okay? Even though they have the same period, these are all periodic waves, those two are non-simple harmonic and the form differs from each other. You can hear the difference. Maybe this is one piece of instrument and here is a different type of instrument that looks just different. I mean, actually, the sound just different. Okay, as a matter of fact, on page 566, you have a diagram like that. The first one is a tuning fork. This one was intended for flute, and next one is intended for clarinet. You know, of course, if you can use flute and clarinet to play the same tune, you can still tell, okay, no, this sounds different. It sounds like a flute, and here it sounds like clarinet. They are playing the same tune, so T is the same, okay? They're all periodic functions of the same period, but they sound different because they have different waveforms. Using Fourier analysis, I must use the same base frequency, fundamental frequency, and the higher frequencies for all of them because, again, they have the same period. Okay, but to mimic the difference between this wave and that wave, what you need to do is you have to choose A1, B1, A2, B2 differently for this wave and that wave. Okay, but as long as you choose A1, B1, A2, B2, and so on correctly, you can produce a wave like this, exactly like this, and produce a wave exactly like that. Okay, so this is to say any periodic wave is always can always be represented by a whole bunch of sine and cosine, in other words, simple harmonic waves. And this procedure of breaking down any complicated periodic wave into a series of sine, cosine functions of those frequencies, it's called Fourier analysis. And each term is called a Fourier component. Okay, let's take a look at page 567 in the textbook. Using the same three waves that we studied before, tuning fork, flute, and clarinet, this time we plot the so-called Fourier spectrum. Okay, what's a Fourier spectrum? Basically, you know, each of these non-harmonic waves is a sum of a whole bunch of sine cosine waves, right? Each one is called a Fourier component, remember? And this is the tuning fork spectrum. A spectrum means how do you break it down into different Fourier components. Okay, this is a tuning fork. A tuning fork produces a pure sine or cosine function. So you only have one term. Okay, you only use a single harmonic term. You don't need the second, F2, F3, and F4. So therefore, you only have one line here. The sound is pure but boring. Okay, here is the flute. For the flute, you have F1, but you also mix in a little bit of F2, a little bit of F3 and 4, and so on. By the way, F2 equals 2F1, F3 equals 3F1, and so on. And if you mix them according to this kind of proportion, okay, in fact, here F2 is the largest. It's even greater in amplitude than F1. It's going to sound like a flute. Okay, now, next one is clarinet. With clarinet, playing the same tune, you're going to have the same Fourier components. You're going to have the same F1, F2, F3, and 4, so on, right? But why does it sound like a clarinet instead of a flute, even though they're playing the same tune? It's because the spectrum is different. Here, the second F2 component is rather low instead of rather high here. So the first one is pretty high, but look at the fifth one. Okay, this is F5, okay, which is 5 times the frequency of F1. It has a pretty high amplitude. So when you use simple harmonic waves F1, F2, F3, F4, 5, and so on, mix them in with this kind of relative amplitude, it's going to sound like a clarinet. This tells us in principle how to make electronic keyboard. You know the electronic keyboards, right? You can switch to different playing modes. You can mimic a piano, a violin, anything you want, right? How does the same piece of electronic instrument mimic all these different types of sounds? Well, the principle is rather straightforward, and that is you must obtain the Fourier spectrum for each of these musical instruments being played. For example, if you want the thing to sound like a flute, okay, then the first thing you have to do is to find the Fourier spectrum for a flute, and which will look briefly like this. Okay, I'm copying a diagram from the textbook on page 567. The first diagram on top, the middle one on top. Okay, so it's just like this, right? This would sound like this. So here's F1, F2. Remember, for the flute, F2 is largest in amplitude, and so on. Okay, so what you do is you design a computer chip. Okay, this computer chip will mix different frequencies in at this kind of proportion. If you want this thing to sound like a flute, you want the strongest amplitude for F2, which is twice as F1. Okay, and the rather strong amplitude for F4, and so on. You mix them with this kind of proportion, it's going to sound like a flute. Of course, these are 1, 2, 3, 4, 5, 6, 7. There are more, afterwards. Okay, so what is the difference between a good electronic synthesizer or a mediocre one? Well, a good one uses even more. Okay, you keep on going. So you have basically more terms from the Fourier series in order to have a more detailed representation, more faithful representation of the Fourier spectrum of the flute. But if you fully analyze the spectrum of the flute, and if you put all these frequencies in, you don't miss anything, put all of these in at the right proportion according to this diagram, it's going to sound indistinguishable from a real flute. Okay, so if you want to play, if you want to sound like a clarinet, and then what you do, you go back to the diagram of the Fourier spectrum of a clarinet. Okay, so you adjust the relative, use the same F1, F2, F3 because it's the same tune, right? But you readjust the relative amplitude of F1, F2, and so on, using that's of course controlled by the computer chip. So that is why the computer chip, using the Fourier spectrum, by mixing these frequencies in, you can produce whatever kind of musical instrument sound that you like. Okay, what we have here is also is another rather stunning example of how, using the appropriate Fourier components, you can get whatever periodic wave you want. What we have here is we added 3 only 3 Fourier components. Okay, F1, F2, and F3. There are only 3 waves. Okay. Actually, I'm sorry. Let's take it back. We only have 2 waves. Okay. Here is one wave with the frequency F. Another one with frequency 3 Fs. Okay, so vibrates faster like this. Now we add these 2 waves up. What we get is this red wave. Okay, this red wave. This red wave we don't recognize as anything special. But it is not harmonic anymore. Okay, it doesn't look like just smooth up and down anymore. Rather, it's like it's up and then down, then up and down like this, right? This is the result of adding 2 waves up, one with frequency F, the other with 3F, with of course the correct amplitude. Okay, now what happens when you mix more Fourier components in? So this time I have 3 waves. Okay, I got 3 waves: F, 3F, and 5F. I added one more. Okay, I have a 5F. So this is the new one. Okay, this is the newest one with the frequency 5F. This time, by adding all these 3 up, I get this green wave, which is the result. This green wave looks kind of like the red wave, except, it stays flatter at the top, flatter at the bottom, flatter top and flatter, and goes up and down rather fast here. Guess what happens if I continue this trend? Well, this time, I'm going to add even more. 1 component, then 3F, another one, 5F, 7F, and 9F. I add 1, 2, 3, 4, 5. I add 5 Fourier components. I add them all up. Here is what I get. Look at this resultant blue curve. This blue curve is almost like a square wave. You see? So you wonder, how is it possible to use smooth sine cosine waves to get sharp edges? It turns out, yeah, you can actually do that. All you have to do is to make sure you put in the right frequency, arrange them with the right relative frequencies. Relative amplitudes. Okay? That's Fourier analysis. In fact, what you have here, you still get these wigglings, okay? It's not perfectly straight at the top and the bottom. The reason is because we only added the first 5 Fourier components. There is 1, 3, 5, 7, 9. There's 11, 13, whatever. You keep on adding, okay? You keep on adding. Then you find the more waves you add, the smoother it's going to become at the top and the bottom. Eventually, you're going to get sharp edges. Exactly like that. So this is a stunning example on how you can use Fourier analysis to get pretty much any periodic wave, including those very sharp edges, in other words, square waves. Okay, let's look at a sample problem right now. Will be sample problem number 9 on page 571, chapter 18. What we have here is a pole, and on the pole there are a pair of speakers, identical speakers. They're driven by the exact same frequency, and the frequency is 200 hertz in the air. The speed of sound is 330 meters per second. The poles are apart from each other with a distance d, which is equal to 4.00 meters. Okay, it says a man walks from far away and gradually moves towards this pole. The distance between him and the pole at any given moment is L. Of course, L is a variable. Now the question is, as he walks in, he's going to hear sound maxima and sound minima. They're looking for the location, his location, in other words, the value of L, when the sound is a minimum. Okay. And they're asking, what is the value of L? Actually, how many of these locations are there? How many different values of L are there, such that when he's a distance L away, he hears an intensity minimum produced by these 2 sources? Okay, the idea is very simple. Basically, what you do is you realize that he hears 2 waves of the same frequencies, and they're coherent waves. Okay, one has to travel this much distance before reaching his ear. Another one has to travel that much distance. Okay, here is source 1, here is source 2. This distance is x1, and that distance is x2. They have the same initial phase, so the phase difference between this wave and that wave upon reaching his ears, delta phi, that is what we need to know, right? And delta phi, as we know, equals to 2 pi over lambda, that's k, right? And then delta x. If we want an intensity minimum, then we want these two waves to have destructive interference at that location. In other words, we want delta phi to be an odd multiple of pi, okay, 2n plus 1 times pi. Here n can be any integer, right? This is the condition for destructive interference, in other words, a sound intensity minimum. This is the same as saying that delta x equals n plus 1/2 lambda. Okay, you have n lambda, which will be of course in phase, but you have another additional half a lambda that reverses the phase, so that it will be out of phase if delta x equals n plus 1/2 lambda. Here n can be any integer. Okay, we have to make a little assumption here. Based on the drawing from the textbook, let's assume that this lens is pretty much horizontal. Okay, in other words, this angle is pretty much 90 degrees. That simplifies our calculation. Otherwise, you have to know, how tall this pole is from here to there and how tall the person is. Then you can find this angle, but that's more complicated. So delta x is x1 minus x2. So let's work it out. Okay, this is x1 minus x2. What is x1 and x2? Okay, x2 is just L, right? So this is just L. What about x1? x1, look at the right angle triangle here. This is the hypotenuse, right? This length is L, that length is D. So isn't it true that this is just L squared plus D squared, right? And you minus D, of course, minus L, of course. That is delta x. We want to make sure that delta x equals n plus 1/2 wavelengths. We're looking for the values of L that will satisfy this equation. There's one little trouble here, one little piece of trouble, and that is we don't know what n is. Okay, we know it's an integer, but I don't know exactly what kind of integer it is. So if you can find, say, 5 different values of n, which will make it work, 5 different integer value of n, that means there will be 5 different locations where he hears a sound intensity minimum. How many allowable n are there? Well, let's do a little calculation, shall we? There is a square root. I don't want that, so what I'm going to do is I'm going to move that L to that side. Okay, I'm going to move that L to that side, and now I only have the square root on this side, and then I'm going to square both sides. Okay, very simple algebra. And if you do so, you will get, on this side there's only L squared plus D squared. Remember, the square root is gone because you took the square of that side. So you get L squared plus D squared, right? What does that equal to? You move that L over there, and you took the square root, and you took the squared, so you get L squared, right? Plus the middle term is L times 2n plus 1 times lambda. Okay, move that 2 inside, okay? And then, of course, you have to square that term as well. So the next term is n plus 1/2 squared lambda squared. Okay. The nice thing about this is that now we can cross out the quadratic term, L squared. So this is just a linear equation for L, which satisfies the condition for minimum interference. So we can solve for L, okay, easily. And here is the value of L if you solve for it. It is equal to D squared over lambda times a factor. And here is the factor here. If you solve for it, 1 minus, okay, n plus 1/2 squared, and then lambda over D squared divided by 2n plus 1. You see, with different integer values of n, I'm going to get a different L, okay? Each integer will give you a different value of L, but whatever happens, you want to make sure you choose such an integer such that L is never negative, right? Otherwise, that doesn't make any sense. L can vary between 0, which is right here, to infinity. But you see, this is 1 minus, right? So as n increases, chances are that the second term will exceed 1, and then you're going to have a negative value for L. So the question is, what is the maximum value of n, integer values n, such that this remains positive? Okay, this will be the largest value of n that's allowed for a reasonable solution. To do so, we need to find what lambda is. Okay, lambda is very simple. Lambda is v over f. Okay, v here is 330 meters per second. And f is 200 hertz according to this Prob statement. So this is equal to 1.65 meters. And d equals 4.00 meters. Okay, so what you do is you plug lambda plus plug d in. You know what this ratio is, right? And then you make sure, okay, that you find the value of n such that n is not too large, so that this next term is less than 1, so therefore L stays positive. It turns out that if you do so, you find there are only two possible values of n, which is n equal to 0 and n equal to 1. So for L to be greater than 0, n can only be 0 and 1. You can easily see it for yourself. If you plug in n equal to 2, okay, if you plug in 2, and then you plug in lambda and d, it turns out you can check numerically that this second term is going to be greater than 1, which means you're going to get a negative value for L. So now it's established there are only two locations as he walked from infinity all the way to the bottom, to the base of the pole here. He has only two locations where the sound intensity he hears is a minimum. One corresponds to L equal to 0. The other one corresponds to L equal to 1. I mean n equal to 0, n equal to 1. Then all you have to do now is to plug in n equal to 0 to get the first location. Plug in n equal to 1 to get the second location. Okay, the algebra then is trivial. And if you did so, you'll find that so the first value, L, equals to 9.28 meters. That corresponds to the case when n equals 0. Okay, the second one is 2.00 meters. That corresponds to the case when n equals 1. So when he is 9.28 meters away from the base, he hears the intensity minimum. And the second time when he moves further in at 2 meters away from the base, he hears the other intensity minimum. And there are no other intensity minima in between, wherein the two speakers are totally out of phase. So again, what we did here was we understood that in order to have an intensity minimum, you must make sure that these two waves interfere destructively, in which they're out of phase, in which delta phi equals even odd multiple of pi. So delta x equals to n plus 1/2 lambda, and you just find delta x geometrically, and you go for it. You find that there are two such locations. Let's look at one more sample problem, number 42 on page 574. What we have here is a tube of water. Water is being introduced into the bottom of the tube at a rate of R. That's the volume rate at which water comes in, leaving an air gap between the top of the tube and the bottom at the top of the water of length L. This is equivalent to an air column with one end open and the other end closed. Now, what if I use a tuning fork to cause some vibration of air column inside with a fixed frequency F? If the lengths of the air column from here to there satisfy resonance conditions, such as this situation, that situation, with an antinode of displacement at the closed and open end, and zero displacement at the surface of water, which is the closed end, then you can have a resonance, right? Now remember, this time the situation is different. We have a fixed frequency and therefore fixed wavelengths for the sound, but we have variable L, variable lengths. As water is being added into it, the length shrinks, right? As the length shrinks, it's going to pass through successive resonances. In fact, here's one resonance with 2.5 loops. Okay, now as water is being introduced, the water level goes all the way up from here to there. You can hit the next resonance, right? So you see, as you go from one resonance to another, the water has to go up by a distance delta L, which is one loop or half a wavelength. And what they're asking for is the time it takes between one resonance and the next resonance. Okay, from our analysis, this is also the time it takes for water level to rise by a distance of half a wavelength or one loop. So how long does it take to do that? Well, you know, the volume at which water is added, the rate at which the volume of the water is increased is R. So delta V over delta T is equal to R. Okay. Now, what we want is we want to add this much water, right? So that the water level can go up from here to there, to go from one resonance to the next resonance. So in our case, what is delta V? Delta V would be equal to this much volume of water, okay? Which is equal to the area of the cross-section, times delta L, okay? Delta L divided by delta T, right? Okay, area, you're given the radius of the water column, and therefore you have pi r squared as the area, times delta L, which is, as you know, half a wavelength, this one loop, and divided by delta T. What's delta T? It's the time it takes for water level to rise from here to there. It's also the time it takes for resonance, for this resonance, and then you go to the next resonance. So that's the time difference between successive resonances, which is what we're looking for. So we find delta T to be equal to pi r squared lambda over 2 divided by r. Okay, and of course you're not given lambda, rather you're given f. So lambda equals the speed of sound divided by f. You plug that in, you'll find the time it takes between two successive resonances.